professional learning sessions!
The reason we call this nature and practices is that they're two different aspects. So the nature of science is what is a scientific way of knowing? How do we get scientific knowledge? What is it? What characterizes specifically the kinds of knowledge that we call science? And then the other piece is the practices of science. How is it done, right? So we're going to have both of those aspects covered in this session, and some experiences that are also related to how to invite students into understanding those things. Do a fist bump with the person across from you, and they are your partner. Wait, you're my partner. Oh. You're my partner. If you are conducting this activity with students and or field naturalists, you should be part of the thought swap as well. You will find out a lot by doing that. It is a good thing to do. What's going to happen is I'm going to give you a prompt, and you'll only have about a minute to share, to discuss that prompt. And each person needs to have time within that minute to share some ideas. So if you use up all the airtime, you're not such a great partner. You need to know how I will stop you from talking after a minute. This is the amazing technique that works really well with students, and it's amazing how fast they catch on to this. It's called the touch of silence. I will demonstrate the touch of silence. We will do the touch of silence. We'll see how quickly we can pass it on. So the question to discuss right now is, what is science? What the heck is that stuff? Talk. Oh, you're on.
Objective processing and observation.
Science is making observations.
I also just think that it's so perfect to use the environment. So if we're at a residential center, we don't have to, when I was in the classroom, I had to bring things into the classroom.
Yeah.
And so when I'm outside, it's there. Like, I don't have to bring anything in.
Yeah, you're not scooping in little water striders and bringing them in. They're actually out there discovering, and they're finding it for themselves.
I think residential EE centers have an opportunity to give the intense, life-changing, immersive experience that schools don't always get to.
And we have the best classrooms in the world. Like if we're gonna do science, let's do it like where it happens. I think we're doing them a disservice if we're in these environments and all we're doing is like team building and leadership and adventure, and we're missing that piece of science.
The science you do at an EE residential center should be the science that you can't do in a classroom.
I want you guys to read the word and then tell me some other words that come to mind. What else you think of when you read this word, okay? And the word is, my handwriting is not very good, adventure. What else do you think of when you read the word or hear the word adventure?
Going into the unknown.
Wait, hold on.
Escape. Awesomeness.
Wait, guys. I'm going to replace this word with another word and make the claim that all of these words still apply to it. Are you ready for that? The word is, that's hard to read, science. So I'm not going to ask you right now, but at the end of our student activities, I'm going to ask you to tell me if you agree or disagree that science can replace the word adventure and these words still apply to it. Okay, so for right now, what I want you to do is turn and talk to the person next to you, just one person next to you, about what it is that scientists do.
They ask questions and think through thoughtfully how to go about finding answers.
Right.
It's a process of
Bring it back in here.
moving towards greater understanding.
All right, so I've just put out in the center here a small poster that could be larger that says core field science practices. And practices are the things that science practices are the things that scientists do every day in all of their work, right? And field science practices are the things that they do outside when they're in the field. What do these mean? So I'm gonna ask Chris, what are some things that you notice about this? What do you notice?
Well, it's
And
got
Christine, jump in there, and Eric, jump in there too.
it's got lots of holes in it, and some of them appear to be in straight lines.
They're all around the same size. There's not a big difference in size of the holes.
Great. So Chris and Christine have already started observing and exploring. That's the first two practices, right? So Sarah, Andy, and David, what are some questions you have about this?
Where did those holes come from?
Awesome. So these guys already are starting to ask questions. That's another field science practice, right? All right, Allison and Annie, what does this remind you of? Have you ever seen anything like it before?
Reminds me of maybe something that termites were in.
Some of it looks kind of like a beehive almost.
Already, they're making some connections to what they already know, to what it reminds them of, right? They don't not necessarily know what it is, but they're connecting to what their prior knowledge, right? You guys are making connections. Easy enough, right? All the things we just did are part of discovering science mysteries, right? If you look at something with a scientific perspective, all of a sudden any rock on the ground, any stick on the ground, any log becomes a science mystery. And what scientists do is try to figure out what those science mysteries are and discover them. So Jenny and Candace, do you guys have any ideas about what this might be? Can you make any explanations?
Some kind of, I think, some kind of animal or critter might have made these little...
What's your evidence for why you think it might be an animal?
Well, I have seen these before.
Yeah.
I've seen, like sapsuckers, for instance, will poke holes into the bark and eat the sap. And I've seen some beetles and stuff.
Does anyone have any other ideas about what this might be or any other explanations?
There's certain kinds of bees that bore into wood.
So already you guys are making evidence-based explanations. So these science practices, these are things that we're going to be doing all week at Outdoor Science School. And what I want you guys to do is to really pay attention as we're going through these activities to what science practices you're doing and to think about, are we doing any more besides the ones that are on this sheet right now?
We're going to do a scientific investigation to look into this. There's some other ways we could look at this question. We could read to see if anyone else has done a study on it. We could just think about what we think might be true. We could just kind of walk around and look at stuff. But we're going to approach this like scientists. We're going to be careful and we're going to see what we find out, okay? You all are going to get the chance to move around and explore and try and find as many different kinds of spider webs as you can. Here's the deal though. We're not going to touch any spiders individually, and actually very few kinds of spiders cause any harm to humans. So don't worry about that. You're just going to be looking at different kinds of spider webs. You'll find a partner and you'll head out there and you're going to find as many different kinds of spider webs as possible. Make observations about them and compare them to each other. So look at different kinds of webs, think about how they're different, and think about how they might be used to help spiders catch different kinds of prey. We also have one more tool. This is a spray bottle, and one person is going to be the operator of the spray bottle. What they're going to do is go around, find a spot where there might be some spider webs, and then mist it a little bit, because that helps the spider web show up a little more. The deal with this thing is the person who has it has to be responsible. They can't spray people or destroy the spider webs.
It's like a bed almost.
It is. It looks really soft.
And it's supporting the water droplets.
I wonder if the water droplets, what they do.
Where did you find the most webs?
On plants.
Okay. What about the least webs?
On the ground.
High traffic. Okay. Anything more specific than just plants or not plants?
Edges.
Okay.
On the outside parts of the plants.
On the outside parts of the plants. Okay.
Hidden or protected, semi-protected areas, like in the groove of the bark of a tree, like at the base where all the reeds are coming out.
Nice. We need to be careful about what we're doing. We need to act like scientists if we're going to do this study, okay? As scientists, we also try and be aware of bias, okay? Humans are biased. It's okay. And what people do is they often look for information that proves what they think to be true.
I would want to make some kind of sample area that was the same size and survey how many are in these 3 random foot by foot squares in the forest versus the meadow or something.
These, I see lots of little fluff from plants, but
that leaf is in.
Skunk.
Oh, I think. No. Oh, come on, I gotta find something. Here's the bias in me coming out. I said meadow. I want to find
You said
something.
meadow?
Yes. Being proved wrong. No.
Now see, we have bias right
Oh,
now.
absolutely.
Something that scientists try and think of too when they do studies like this is this really what's going on? And they do that by thinking about the study they did and thinking about what are flaws in our study? What could we have done better? If we were to be scientists and do a really long study on this, what would be your experimental design? What are the challenges of doing an experiment like this? What information can't we get?
Even though there are lots of problems with it, I mean, our results, there's a really clear pattern that was pretty remarkable.
Yeah, we still know a little more. You know,
Yeah.
we know a little more about the world. But just kind of one thought on the activity is that it kind of matters less about getting the answer and coming to the answer, and there's a lot of value in giving students the experience of the struggle of coming up with a study and the experience of being like, oh, that wasn't super accurate.
So I showed you guys earlier this morning this list of, or circle of core field science practices. I want to show you a couple other types of science practices. So we've got our applying and communicating practices right here. Actually, I'm going to switch these. Applying and communicating over here. So that's stuff like sharing out what you find with other people, using models, solving problems, critiquing ideas. And then over here, we've got our investigating practices. That's when you plan an investigation like we just did. Collect data, analyze that data, maybe use field guides and resources. Do you guys see practices on these two additional ones that you just used? Does anyone see? Yeah. Turn and talk to a neighbor about what sequence did it go in? What was the order that you used these various practices?
We came up with that research question, right? And then we went out and we collected data. We made more connections.
We also planned an investigation together. We collected data, and then we did a little bit of we interpreted our data.
Yeah.
We did use field guides and other resources.
What were some of the things you guys noticed about the sequence of using these practices?
Well, I thought we sort of focused on this first bubble this morning when we were out exploring. And then it kind of went back and forth after that once we started to think about the investigation.
Did other people notice this kind of back and forth thing? Cool. So, yeah. When these are like one solid poster, which they usually are, these arrows match up, and they're all double-sided arrows. And the reason that we do that is because when people are really doing science, there's no one scientific method. There's many scientific methods, and you start here and you go there and you come back. And so we use those double-sided arrows to kind of show that when we're doing science, we're doing a bunch of different stuff, and we're doing it as it's needed and whatever is going to fit the purpose of what we need, right? So if you guys were kids, I would come back to the science adventure thing and talk about that a little bit. But what I want you guys to reflect on and maybe just write down in your journals for 2 minutes is what are the scientific practices that the students in your programs, what do they get really good experience at? And what do you wish they could experience better?
Handing out another resource for you that is similarly taken from a lot of different sources and compiled in a way that we think makes sense to educators of all stripes. Look it over a little bit first and react to it, whatever you think about it. But a little bit of reflection on whether any of these aspects of science were modeled in some of the activities we did outside. I want you to just read it through a little bit by yourself, and then we'll discuss.
I've also heard that science is a study of the natural world.
So do you know what they mean by natural world?
I'm not sure exactly.
So I've talked
but I've heard engineering is sort of a different kind of science study, but so I'm not sure.
It is. No, that's a great question, because oftentimes people hear natural world and they think of nature, right? The natural world is anything that can be perceived and or collected evidence about. So the distinction is the supernatural. It's not the supernatural. Engineering is how we apply what we learn in science to solve problems and or design solutions, or design things, right? Would you agree, Miss Engineer? Is that what engineering is?
Yes.
And a lot of environmental solving of problems is engineering as well. I actually think it's really important to contrast it to other ways of knowing, like supernatural ways of knowing, in contrast to faith-based ways of knowing. We have actually worked with some Catholic diocese organizations that get a lot of kids from there, and it's something that they just need to be really clear about. We're doing science now. It's very different from other kinds of ways of describing the world.
So we started to try to define science a long time ago, and it surprised me how hard that is to do. And we went to lots of different book resources. We interviewed Kevin Padian, who was one of the witnesses at the Dover trials. So he's an expert on science, and some of his words are in the document you see there. But one of the things that really struck me was that's part of what science is, actually. It's not any specific anything. It's what works. What the community at that moment agrees is the best way to investigate something, and the scientific method that somebody uses, any individual scientist uses to investigate a question, is what makes the most sense for that question at that time with the tools they have available. And they're constantly picking at each other's investigations and methods and all this, always trying to come up with the best way to get at the most accurate response. But that's what it is. It's more of an endeavor for a goal, an unachievable goal that they recognize as unachievable. It's confusing.
We're dealing with as a public and even policymakers who want science to be monolithic.
It's hard to understand what it is, right?
Or the opposite. Science is evil.
Yeah. You probably noticed that the investigation was not organized like this. This is such a pervasive thing out there in school districts.
The teachers that I've worked with sometimes get really caught up in the order, and it has to go in this fashion. You have to say these words in order to be doing what they want you to perceive what the child is doing. And we actually recently had a teacher professional development where the presenter totally blew these teachers' minds, but was like, you don't have to start at the question. You can be tootling around and experimenting, and then the question comes up at a later date. Kind of what we've been talking about today, how it can be, you can kind of start anywhere on the circle. And I think it puts the scientific process in a box sometimes for teachers, and it's hard to get them out of it.
It's not the scientific method, it's a scientific method.
So much of what you model already is getting the kids curious and giving them enough content to arrive at the question. So how do you start with that when if you don't have the curiosity yet?
And those of you who are field scientists, is this something that commonly happens outside in field science?
I actually use this a lot.
We argue about this a lot.
Yeah.
I'm anti-hypothesis. I did science for a long time, and the only time I came up with a hypothesis is when I had to do statistics. Often we were going to the field, we knew so little about what we were investigating, we didn't even know enough to come up with a genuine hypothesis statement. So
yet we asked 9-year-olds to do it.
Yeah, exactly. Yeah. I think Doc's done a really masterful job of blending or working in what is a very familiar process in with a bigger investigation framework, so that there is that comfortability for the educators that we're working with, that we're serving, because this has to be relevant to those educators, otherwise we're dead in the water. And so I don't necessarily agree with the word hypothesis, but I'm okay with it the way Daksha frames it in her practice.
In a lot of our formal school settings where we teach students how to be linear thinkers, and that's my kind of struggle with the scientific method as it is up here, is that it's a very linear progression. And kind of thinking about it as a cycle or a circle of scientific logic enables those thinkers who think in a different way to come into the process at any point.
We had a almost 2-year-long debate on this just over experiment, not hypothesis. because in Texas at 5th grade, we're supposed to introduce an experiment with one variable. And when we defined experiment, you pretty much cannot do an experiment in the field because you can't isolate things down to a single variable.
And the contrast is the systematic observations that are more common in field science, where you don't have a control, you don't have a variable that is your outcome variable and a test variable, but much more systematic overview of collection of data over time, looking for change over time. We're offering an alternative for those who want to use it, and you saw it. What we're saying is that we could represent science as more of a fluid process where these arrows don't go in a particular order. It is applies entry points for different kinds of learners, but also it allows us to kind of focus on some of those field practices that we think are more commonly accessible for students out in field experiences. But we think that it would be nice to focus on those ones over here as a way in to being able to communicate with teachers too. Because that's the other thing that we want to be able to say to our students, that science doesn't fit into a box, and that we could use this sort of diagram to show that these are all valid practices of science. It's the way scientists figure out and explain the world. It's not a fringe idea that we should be communicating that there are many methods. Yeah. And teachers are hearing it. Teachers and districts are hearing it. That scientific method thingy that we teach to kids that's been around forever and ever and that teachers are really invested in, I don't know, do you all know where it came from? This guy decided to interview scientists and take a tally of the methods that are used in science, and he interviewed many scientists, and he collected those processes that were identified by actual scientists in practice, in working in science labs, in many different kinds of science too, by the way, and he put all those into a big tally, and he the ones that came up the more times became part of a list that he developed. That's those ones that were on that previous slide. And he put them in a logical order. And then what happened was textbooks and other educational folks got hold of that and decided that this is how we should teach what scientists do. In order to really deeply learn science, this is what's necessary.
Is there sources for that? A series of reports that were produced by the National Research Council at the National Academy of Sciences. But taking science to school was kind of the first in a series that rocked everybody's world a little bit and really summarized the most current research from the last 15 years or so. And then the framework for K-12 science education was largely based on taking science to school.
The stuff that we have in the new framework, the new science framework. And by the way, we're focusing on the framework because the framework is pervasive across the country, even in states that have not yet adopted NGSS, Next Generation Science Standards. It's a really good read. If you haven't read it, it will help you really understand what they're framing as a vision for the way science should be instructed in this country. Basically, all the right people were involved to develop this. That's what we think. And then those standards came out of that. So that's just the framing of where those documents come from.